Today on our bench we have a GIGABYTE motherboard. This board came to me with a no post issue. It would power on, but there was no display output and no LED lighting at all. It took me about 5 days to track down the culprit, and the cause turned out to be very unusual. That's exactly what made this repair so interesting. It really forced us to look at the repair process from a different perspective. We'll be restoring multiple traces, soldering knocked off components, almost replacing the VRM controller, and doing lots of soldering work, as usual. So, get into a comfortable position in front of your TV, grab a cup of something nice, and let's go! Hello everyone, today on our bench is the GIGABYTE B550 AORUS Elite IX version 2. This is a solid gaming AM4 motherboard that came to me with a no-post issue. According to the customer, it powers on the fans pins, but there are no LED lights and no boot. Let's try to investigate the issue and see if we can bring this board back to life. As usual, we'll start by measuring the resistances on the main power rails. So 3.3 volts, we have 423 ohms, 5 volts, it's kilo ohms, 12 volts, it's also kilo ohms, 5 volts standby power, 5 USB, it's 134 kilo ohms, minus 12 volts, there's nothing here. Main coils, I guess this is 1.8 volts. So kilo ohms, let's do memory. Memory coil 900 ohms. And this is a PCH power coil, mega ohms. Okay, way too much. What else we have here? We don't have any open, so we can just check the V core. It's 47 ohms without CPU. Then the CPU, it's 91 mega ohms. And CPU to V core, just to be sure that 12 volts is not shorted to V core, and we can put the CPU safely there. So it's 53 mega ohms. Okay, and our 47 ohms for V core. Perfect. So basically we can try to power it on. For this test, I will use Ryzen 3200G AM4. CPU is in place. Now power on. And 107 milliamps. This is healthy. Pressing power button. And we have just partial power consumption. So there's no V core, I guess. 500 milliamps is just basically a standby and 1.8 volts, I guess. Let me check within the multimeter. What do we have? And we have 2.5 volts for the memory. Okay. There's nothing here. I guess we measure right here. 0.9 volts. This is a CPU. And what about leg number 8 of the BIOS? 1.8 volts present. For sure, there is no V core within this consumption. There should be 5 volts, 5 volts, and that's it. Other voltages are covered by heatsinks. I guess we need to disassemble the board and to make a visual inspection under the microscope. for this red mark here, like an exclamation point. This is clean. There's no signs of blown MOSFETs. What is that red dot here? Does it mean that it's not working? Looks to me that this board was already serviced somewhere, because all of that red marks are very concerning. Let's look at the microscope. So first I would like to see the thermosis, the VRM area. And so there's nothing critical. Okay, what about the PCH? Do you see that red dot? I don't know, what does it mean? This is kind of concerning because during the manufacture, usually no one marking the PCH. But it looks like this dot applied before applying the thermal paste. So now it's much better. Okay, right here we have an SAO chip. I don't see any damaged components near the SAO. The SAO looks good. Here is memory protection, memory voltage, and CPU voltages. And I don't see anything critical. So usually those markings are made by the manufacturer, and it means that this chip was pre-programmed during the manufacture or after the manufacture and mounting here. So this is like a quality mark that it has been programmed. Let's see the flash BIOS chip, and the BIOS chip looks nice. I don't think it was desoldered. Looks promising. Okay, what's here? Here we have a network controller, and the audio controller is over here. CPU area. And I already see here that there is a knocked off capacitor. So right here. And this pad with this trace is basically also dismounted from here. This is not critical. The motherboard can run without it. Oh, I see. So there's more damage on the back side of the board. And those caps, those are not filtering caps. You see that there is a signal pairs goes. So these caps are high frequency filters, all right? And so I see that here we don't have pads as well. So those pads they need a restoration. Let's go to the VRM area. And okay, of course. So this cap is the filtering cap of the V-core. This is V-core. And this is critical because without this resistor, we don't have a V-core phase, or we don't have a feedback from that phase. So that means that this phase is not working. And I'm not sure that VRM controller will assert power good signal without this resistor. So, okay, there's no cap. What else? Right here as well, there's no cap. Those caps both are, okay, this is knocked off here as well. Okay, that's the damage. And this is smashed or blown. I'm not sure. Looks like it's smashed. Okay, this area is intact. There's no damage, at least something. What about the under PCH? So this is area under the PCH, and okay. We have a mass over here as well. So that's a lot of components. Those caps, right? Yeah. This is a capacitor. I don't know what this element is. Could be a cap, but could be an inductance or resistor. There's caps, so highly bad that they short the paths between them. So we have a lot of components absent here and damaged, and this knocked off resistor from one of the VRAM MOSFETs. This is a critical part, and so I guess that we have to try to solder them on, to repair it, and try to see if it helps. Because I guess because of that resistor, we cannot get a power good from the multi-controller, and our multi-controller does not provide PWM signal, and those V-core MOSFETs are never start. So there's no CPU power. So let's do it. The first thing we need to do is clean the pads and remove the remaining parts of the knocked off components so we can install the new ones.
we move on to restoring the knocked off pads, we need to expose the traces and solder new pads to them. I'm using trace pads with a thickness of 30 micrometers, which is basically about 2 times thinner than a human hair. I apply UV solder mask to keep the traces and pads in place. It also protects them from damage and prevents short circuits.
Okay, let's see if all that work pays off. Okay, let's power it on. Pressing the power button. And yes, it's working. Now it's 2.6 amps. Wow. And LEDs light up. Okay, let me connect the HDMI capture card to see if we have any changes. Okay, HDMI connected. Now I need to show you the post screen. Okay, let's try again. Yeah, it's powering on. It's almost booting. Okay, 2.6. 2.3. Well, we have a post screen, 4 amps. Okay, and we do. Finally, so the board is alive. I'm so glad to see this. So much work has been done. So what have been done to this board? There were a lot of knocked off components on the back side of the board. So I had to remove all damaged capacitors from the back of the board, restore traces of differential pairs used in PCI Express signal lines over here, solder it knocked off resistor used in VRM current sensing circuit. This is line number 4 right here, right where the exclamation mark was. So do you remember that exclamation point? It was painted right on the MOSFET number 4, as I remember, which has this knocked off resistor. I guess someone has already tried to fix this board and found no connection on current sensing pin of this MOSFET, but couldn't figure out how this happened. Okay, what else has been done? It was soldered the most of the V-core filtering, as well as caps in the CPU area. I even refreshed BIOS within the programmer. I measured the voltages on the VRM controller, and this controller has one enable signal and 2 power good signals. The enable signal is called CPU VDD enable. It's one of the steps in the motherboard startup sequence. This signal tells the controller to start the V-core and SoC power rails, which are the main CPU power lines. In this case, both power good signals were low, so I initially suspected that one of the SoC MOSFETs might be failing. There's 2 SoC MOSFETs, number 1 and number 2. In this case, both power good signals were low, so I initially suspected that one of the SoC MOSFETs might be failing, specifically the 2 MOSFETs on the right side. However, after measuring voltages and resistances across all the MOSFETs, I couldn't find anything unusual. Everything looked perfectly fine with no signs of damage. Then I remembered that one cap was missing, and I found that it should be located right under the VRM controller. The VRM controller and the cap from that side. So this cap is a regular bypass capacitor used to filter the internal voltage regulator inside the controller. After soldering this cap back in place, the board finally booted without any issues. I think it's also worth noting that manufacturers don't provide datasheets for components like this. They are most likely made exclusively for motherboard manufacturers, which in practice make the repair process much more difficult. This is a great example of how a single missing cap can completely stop a motherboard from working. It was the first time I encountered a problem like this. This board definitely deserves a proper cleaning and reassembly, and I hope it will serve just as long, if no longer, than it already has. I guess that's it for this one, I hope. I didn't bore you with the long soldering and restoration process. I tried to keep it as compact as possible. I want to thank you for all the kind words in the comments. They truly inspired me to keep recording more videos. I try to answer all of your questions in the comments, as always. Also, please don't forget to like and subscribe. See you in the next video.